Okay, so good morning, everyone. So, as Ronald says, I'm going to be talking about quantum algorithms for pattern matching today, which is somehow a sort of really classic task in classical computer science, and goes back many, many years. And so it's kind of interesting to see what we can do with quantum algorithms for this problem. Okay, so I'm going to be talking about a very sort of traditional kind of pattern matching problem, which is kind of combinatorial pattern matching in strings. So in this problem, what we want to do is we want to find a pattern within a text. So we have a pattern, which is a short string, well, reasonably short string, like this thing here, string ant. And we have a text, which is a somewhat longer string, like this thing here on the left, quantum. And we think of both of these things as just functions. So the pattern is a function from the integers between 1 and m to some alphabet sigma. And the text is also a function from the integers between 1 and n to sigma as well. And what we want to do is we want to find a position where the pattern appears within the text, as in the characters in the pattern appear consecutively in the text. So, for example, in this case, we'd want to find this position here, where we have ants within quantum, and we want to output the position of the start of this match as the answer to the problem. So, in general, we might have the pattern matching at an arbitrary position in the text, or it might not match at all. And we want to find a match if one exists, and output no match if there is no match. Okay, so that's the kind of traditional kind of text based version. But you can also think about maybe slightly more complicated, higher dimensional versions of the pattern matching problem. So here we have a kind of two-dimensional version of the problem where we're trying to find this smaller kind of binary image within this this larger image here, and hopefully you can see this kind of blue square here, which is where there's supposed to be a match. But we can think about arbitrarily big dimensions d, and this problem still makes sense. So here I'm assuming you have a kind of a sort of square shape text and a square shape pattern, but you can kind of see how one might generalize this further as well. So okay, so this is a sort of relatively general problem, and what's known about its complexity. So to start out with, let's think about this 1D problem, the problem I introduced first. And this has been studied for a long time classically, and it's known that, it's been known since the 70s, that this problem can be solved in worst case time order n plus m. And indeed, this is optimal because you need to always read all of the characters in the pattern and the text to determine if there's a match. So this is very good, it's a very efficient algorithm. And in the quantum setting, there's also quite an efficient algorithm too. So if you were to try and use Grover's algorithm in a fairly kind of naive kind of way to find a match between the pattern and the text, then this would take you order root n times root m time. But back in 03, Ramesh and Vinay managed to do something more interesting and get order root n plus root m up to polylog factors, which is what this tilde notation here means. And indeed, this is also optimal. Like there's the standard lower bound on Grover search goes through, and you have a lower bound of order root n. So this kind of seems like everything you can say about the problem, really. So we have good algorithms which match the worst case lower bounds, but in practice, the inputs that we often receive for problems like this are not actually worst case inputs. They're some kind of average case inputs. And it's interesting to think, well, what can we say about the average case for this problem? Could it be that we can solve this problem more efficiently for most inputs, for random inputs, say? And here what I'm going to think about is quite a simple model for random inputs, where we have every character of the text being picked uniformly at random from this alphabet sigma. And then the pattern is either chosen to be some substring of the text, an arbitrary substring, or it's uniformly random itself, so it's just a random sequence of characters. So in the first case, obviously the pattern does match the text, and in the second case, if the pattern's long enough, then with high probability it won't match the text. In fact, it will be far from matching the text. And for this problem, which maybe models kind of the sort of instances of the problem we might see in practice, can we do better than this? Okay, and classically, in fact, we can do quite a lot better, assuming that the pattern is fairly long. So one can show, and I'm not going to go through the algorithm, maybe it's a kind of fun exercise to try and to think about it yourself, but one can show that this average case problem can be solved in time roughly n divided by m plus square root of n. And indeed, this is also optimal. And again, there are some polylog factors here that I've omitted. So this complexity might seem a little bit strange, but sort of the intuition behind it is that if we have a random pattern and a random text, if the pattern doesn't match the text, it's generally quite easy to kind of certify this fact somehow. You only need to look if you line the pattern up at a particular position in the text, you only need to look at a few positions to be kind of convinced that it's not a match. And somehow this means that you can slide the pattern along the text very quickly. And indeed, somehow it turns out that the longer the pattern, the easier this becomes. And this square root of n bit of the complexity, which again might seem a bit strange, the intuition behind this is that, well, if the pattern's fairly long, then somehow what you're trying to do, or what's even kind of an easier problem than solving the pattern matching problem, is just try and find some position where there's a character in the pattern which is the same as a character in the text, which you need for it to match. And this is kind of a bit like a kind of collision kind of problem, but you get some kind of birthday paradox type square root of n behavior coming in here. Okay, so this is at least if the pattern is fairly large, this is a significantly better complexity than the worst case. On the other hand, it's never better than square root of n, because if m is less than square root of n, then the first term kind of dominates, and if m is greater than square root of n, the second one does. So we always have this lower bound of square root of n, and that's the best you can do on the average case. But in the quantum case, it turns out that we can do substantially better. So the main results I want to talk about today, at least in the 1D case, there's also a higher dimensional case, is the following thing. So modulo some minor technicalities, which I'm not going to talk about, we're going to imagine that the text and the pattern are picked as on the previous slide, so they have this kind of this random choice of text and pattern. Then there's a quantum algorithm which runs in time roughly square root of n divided by m, then times this strange term, which is 2 to the order square root log of m. And this determines whether the pattern matches the text. And if the pattern does match the text, then it tells us the position at which the match occurs. Unfortunately, sometimes it fails. And the particularly, I guess, unpleasant thing about the way it fails is that for some inputs, the algorithm will always fail, or it will be very likely to fail. But for most inputs, which are picked at random, then the algorithm will succeed. So it fails with probability roughly 1 over n, taken over both of its internal randomness and the choice of the pattern in the text. So there are some patterns in text which it just won't work. So just to kind of decode sort of why this is better, this complexity. So this second term here, this 2 to the order root log m, this is lower than m to the epsilon for any epsilon bigger than 0, the scaling there. So this is a somehow very small term. And we've gone from n over m to square root of n over m, so we've kind of got a square root thing here. But the key point is we've not got this additive term here going on. So in particular, when m is quite large with respect to n, like maybe m is order n or m is order n over log n, then we have a kind of super polynomial separation between these two quantities. So this is substantially faster. Yeah, it's a super polynomial speed up for large m in this kind of average case randomized setting. Okay, so that's the one-dimensional case. So in the d-dimensional case, basically everything I just said is the same. So I've just copied the same slide and added some d's in. So classically, the complexity of the average case problem becomes n over m to the d plus n to the d upon 2, rather than n to the 1 upon 2. And in the quantum setting, again, everything is very similar. Instead of being square root of n over m, you get n over m to the d upon 2. And then this term here now has a d to the 3 upon 2 in the exponents. But we're generally thinking of d as being a constant, like maybe 1, 2, or 3. So this isn't so bad. And basically the complexity is very, very similar to the previous slide. Only, as you saw here, only there's some d's in there as well. So the same ideas kind of work out. Okay, so that's the results. So what I'm going to talk about for the rest of the talk is the ingredients that go into the proof of this result. And the main quantum ingredient in this algorithm is an algorithm for this kind of venerable and well-studied problem in quantum computing, the dihedral hidden subgroup problem. or in other words, finding hidden shifts over the integers modulo n. So these colours here are all supposed to be different colours, which may not quite come out on this screen, but hopefully they look kind of slightly different. And the way the dihedral hidden subgroup problem is defined, or at least the hidden shift variant of the problem is defined, is that we're given access to two injective functions f and g, which map the integers modulo n to some set. And we're promised that g of x is equal to f of x plus s for some hidden shift s between 0 and n minus 1. And we want to determine what this hidden shift is. So here you can see that this second function here is a shift of this first one by 1, 2, 3, 4, 5, 6, I guess. Yeah. So here, we should output 6. Okay, so that's what our task is. And it's been known for a while now, since I guess 2005, paper of Greg Kuperberg, that we can solve this problem using 2 to the order square root of log n queries and with a quantum computer. And this is significantly faster than we can do classically, because classically there's a lower bound of square root of n queries. So this is the main quantum ingredient we're going to use. And it's quite tempting to use this, because it kind of really does seem like quite a similar kind of problem, this hidden shift problem here, and the pattern matching problem. They both kind of involve sliding one string of characters along some other string of characters and finding a match between them at some kind of shift. So it's kind of very tempting to try and use this result to solve the pattern matching problem. But there are some kind of gaps that kind of separate these two problems. In particular, the input, the restrictions on the input for this dihedral hidden subgroup problem algorithm are sort of maybe a little bit restrictive. So firstly, the pattern and the text, these two functions f and g that I just introduced, firstly we insist that they're injective, so there's no duplicate values of the functions. They have to be the same length, and they have to be kind of one-dimensional. We're only looking at shifts in this kind of 1D cyclic setting. And yeah, this notion of shift is somehow a bit different, because we're doing shifting modulo n, so we kind of go round in a sort of cyclic way, rather than looking at this sort of shifts where we don't allow this kind of thing. So what we'd like to do is somehow merge these two things, this algorithm and this problem, and relax these assumptions somehow. Okay, and we're just going to go through kind of one by one, relaxing these assumptions. So the first thing we can do is relax the injectivity assumption, because we can just modify the pattern in the text to make them injective. And this is an idea that's been used in a few different contexts. It goes back in the classical setting to Knuth in the 70s, who sketched out an efficient classical pattern matching algorithm based on this idea, but it's also been used in the quantum setting by Garibi and others from 2013 for a slightly different notion of hidden shift problems and of injectivization. But the basic idea here is that we're going to go through our text and our pattern, and we're going to replace each of the original symbols with a concatenation of several subsequent symbols. So the idea is this is going to give us kind of more unique characters in the pattern in the text, and eventually we'll end up making it kind of making each of them injective. So here we're looking at substrings of length 2. So we've replaced this letter Q here with QU, the subsequent letter to Q. We replaced U with UA, because A is the subsequent letter to A, and so forth. We just go along the pattern in the text doing this replacement, so we just get a bigger alphabet. And the important property of this is that if we do this concatenation, this preserves the property of the pattern matching the text. So if the pattern matched the text at some offset, this remains true once we do this concatenation operation. And the converse is true, that if the concatenated pattern matches the concatenated text, then there must have been a match in the original pattern and text. So here we can see in particular that ant matched quantum there, so ant still matches quantum at the same corresponding position. And if we produce a new alphabet by doing this injectivization step, where the symbols in the new alphabet are strings of length k, then we can simulate a symbol to a query to these new strings by querying k characters of the old strings. So we kind of get this overhead of a factor of k if we have to concatenate up to k characters, and for each query that we make. And it turns out that for most strings, it's sufficient to take k being order log n in order to make the text injective. So if we pick every character in this text at random, then even if the alphabet is quite small, like maybe it's a binary alphabet or something like this, we only need to concatenate up to order log n characters at a time, and we get something which, with high probability, will be injective after that point. So this only gives us a log overhead here in our algorithms. Okay, so now we have injective pattern and text. So now how are we going to deal with the fact that the pattern is a different length to the text? Well, this is based on an idea of Kuperbo from 2005, who did something similar for the restricted case where the pattern was kind of exactly half the length of the text and had to be injective. But the basic idea is that we apply the dihedral hidden subgroup problem algorithm to a substring of the text and the pattern, and the substring of the text that we pick is a random substring of the text. So, for example, if we're trying to find this pattern in this text here, we might just randomly pick this position for where as a sort of test case to see if the pattern matches the text there. And we're going to apply the dihedral subgroup problem algorithm to the substring of the text at that position and the pattern. Okay, so what happens when we do this? Well, the point is that if we are quite close to the position where the pattern does actually match the text, assuming that the pattern does match the text at some position, if we are close to that position, then the dihedral hidden subgroup problem algorithm will successfully find the shift where it does match the text at that position. So kind of why does this work? Well, if we look at this text and pattern here, then we can see that we only need to change a couple of the characters of the pattern here to make it match the text in terms of this kind of a cyclic shift notion of matching. So if we change these two things here to green and pink, then the text would match the pattern under shifting modulo m. And if our guess is close enough of the starting position, then we only need to change a few of these characters, and that means that the dihedral hidden subgroup problem algorithm won't notice the difference between this original pattern here and the one with the couple of symbols changed. Again, that's something you'll just have to take my word for, but the basic idea is that the algorithm only makes a few queries, and if the pattern only needs to be changed a little bit to make it match under this notion of cyclic shifts, then it can't tell the difference. So it can find the correct shift with high probability. Okay, and what's the probability of our guess being in this kind of good range where the algorithm does work? Well, it has to be within distance m times 2 to the minus order root log m. So the probability of being in this range is about this divided by n. And using a version of amplitude amplification that can cope with bounded error verifiers, we can find a good position where it matches in this way. So it's close to being the right position of a match. With order 1 over square root this quantity queries, which gives you square root of n over m times 2 to the order root log m. So we just kind of plug this sort of this thing in as a verifier and use amplitude amplification, and this kind of gives us the result. And the time complexity turns out to be the same up to log factors because there's no kind of complicated other processing that's going on. Okay, so that's oh yes, there is one thing I kind of brushed under the rug though, which is that because of this property that the dihedral hidden subgroup algorithm doesn't notice the difference if the pattern's kind of close to matching the text at some offset. It could be the case that the pattern kind of almost matches at some offset, like this one here, but it doesn't kind of doesn't quite match. There are a few positions where it's it's incorrect. It doesn't match up with the text. And so we have to be aware of this, and we have to deal with this when the algorithm kind of returns us some claimed shift. And we can check this using Grover's algorithm. We can basically just find, we can attempt to find a position where there's a difference between what the text and the pattern, once we have a claimed position where it should match. And this gives us an extra term in the runtime, which is dependent on the minimum fraction of positions where a pattern that doesn't match the text does actually differ from the text. So what I mean by this is that this term gamma here will be large if at every position where the pattern might match the text, then you can verify that it doesn't in fact match the text with only a few kind of queries to the two of them. So this is kind of maybe a sort of property testing kind of concept here. And for most random patterns in texts, in fact, this isn't a problem because this term still ends up being lower bounded by a constant. Okay. So far everything I've said is about d equals 1, so one-dimensional things. And there's an interesting question of, can we generalize this to higher dimensions? And in higher dimensions, we want to sort of generalize this dihedral hidden subgroup algorithm that was the basis for this algorithm working. And now our hidden shift S has become a d-tuple S1 through SD of shifts in each different dimension. And we still want to find this shift S. And indeed, we can show that you can generalize this algorithm, and this does still work. So if we have two functions f and g, which are functions from the integers modulo n, like d copies of that, to some set x, and if they're injective and they satisfy this shift property where g matches f up to some shift, then which is now s is now an element of z 2 to the n to the d. Then there's a quantum algorithm which finds this shift with bounded error using roughly 2 to the order root d times n queries. So we get this d appearing in the exponent, but again, if d is constant, this isn't so bad. Okay. So as I'm running out of time, and also taking pity on your jet lag, I won't go through the technical details of the proof of this, but basically it's a generalization of the proof. Or it's a generalization of the algorithmic idea of Greg Kuperberg from 2005 with one or two optimizations which let us improve the complexity a bit and let us get this number 1.781 here in the exponent. But basically, I'm skipping the technical details, but basically the ideas in the original algorithm end up going through without too many changes. So that's lucky. Okay, so just to summarize what I said, there's a quantum algorithm for this d-dimensional pattern matching problem, which is super polynomially faster than classical for most patterns and texts, assuming that the pattern is quite long, which is when you get this kind of super polynomial separation. So as I said, a downside of this algorithm is that for some inputs, which are very unlikely inputs, but for some inputs, the algorithm might always fail, or it might always be very likely to fail. In particular, it might claim a match where there's no match. And the sort of inputs where this will happen is if the pattern almost matches the text, but it kind of fails to match at a few positions. So there's some offset where the pattern's close to matching, but not quite. But at least when the algorithm does fail in this scenario, we know that the pattern was close to matching the text at that offset. So this gives us this kind of notion of approximate matching. So if the algorithm fails, we know that it was kind of close to matching. And what I think is a very interesting question is, can we get an improved quantum algorithm for the dihedral hidden subgroup problem? Because basically any improved algorithm for this problem would feed into this second term here, and it would improve the complexity of this part. In particular, people have looked for algorithms for this problem which run in time polylog, I guess, m here, which so far people haven't found. But I think it's also an interesting question to try and improve the value in the exponent here. So in this big O here, like this is like well, I can't remember quite what the number is here. It's not quite the same one as on the previous slide, but I think it's an interesting question to see how far we can bring down the constant in the exponent. And even if we can't get something that's polylog, it would be interesting to see how far we can go. Okay, so that's everything I wanted to say today. So I'm just going to finish with a quick advert, if I may, that for 2 postdoc positions which are available at University of Bristol, working on the theory of quantum computing, the application deadline for these is the 25th of January, so quite soon, but the start date is flexible. So if you're interested, please do just come and talk to me. So that's it. So thanks very much.
Any questions not related to the job offer?
So if I can take you back quickly to your summary slide.
Yes.
I want to ask about the second point, the inputs where the algorithm might fail. So earlier on you used this concatenation trick,
Yes.
expanding your alphabet to fix one problem.
Yes.
And the nice thing is that this changes some of the properties, but it preserves the property of, perfect pattern matching.
Yes.
Are there any transformations that you could apply? Let's suppose I find a match or a claimed match, but I want to check whether it's a false positive. Are there any transformations I can apply that preserve the property of perfect matching but would break this so that I could, test this more precisely?
Yeah, it's an interesting question. I think my general feeling is that this will be difficult to do. Because if you think of a very simple setting where you have a claimed position, you're just given the information, okay, I claim that at this position the pattern matches the text, and you want to somehow certify the fact, you don't believe me and you want to certify that the pattern doesn't match the text at that position. Then if it only differs at a few positions, like the original pattern and text, then this is going to take you a long time to do, like by standard bounds on kind of unstructured search. So I feel like, those are bounds just on the number of queries to the original pattern and the text you need. So it kind of feels like you can't really cheat by doing some transformation on the original ones, which, unless you're somehow having some other scenario where you're allowing some queries up front which you don't count towards your things later on. Like for example, you might be allowed to pre-process one or other of the two things, which doesn't count towards your queries, and that's an interesting setting which I haven't thought about. But yeah.
One last question.
Is there any formalism in which you take into account that some letters in the alphabet are easier to find, and you start with them?
Right. So classically, in fact, there's a huge amount of work on pattern matching, and people have come up with algorithms which are, which use a lot of different information about the strings, and in particular, if you have many repeated characters or few repeated characters or things like this. Then you can develop more efficient algorithms by using this information. But I haven't thought about it. I'm not sure for this problem if it would gain you anything, because we have in fact matching lower bounds which say that for this problem as I've defined it, this algorithm is optimal up to polylog factors. But it could be, there's a whole world of pattern matching problems out there, and it could be that for some of the others this does let you do interesting things.
Okay, one very last question.
If we consider a special case where n is not too much larger than m, say n is 2m, do you think you can have an easy algorithm that has a cost better than 2 to the square root of m?
Right, so I find it hard to see how to do this without coming up with a better algorithm for the dihedral hidden subgroup problem. So in fact, I wouldn't like to guess whether there is an efficient such algorithm, but it wouldn't surprise me one way or the other. But I think this is going to be a hard thing to solve, because people have looked at this problem for some years and haven't managed to improve this complexity dramatically. But it seems hard for me to solve the pattern matching problem without doing better at this other problem.
Thanks.
Okay, thank you again.
Thanks. Sorry?